This section explores the predict step, the first stage in the predict, compare, learn cycle. We'll examine how data flows through a machine to generate a prediction, highlighting the significance of input data quantity, single data point versus multiple, and its impact on network design. We'll also introduce the concept of a weight, the mechanism that maps input to output in a simple neural network. The core idea of the predict step is straightforward. Data goes into a machine, and a prediction comes out. This seemingly simple process is the foundation of any machine learning model. In its simplest form, a neural network can process one data point at a time. Think of this as feeding the network a single piece of information and receiving a single prediction in return. This contrasts with processing multiple data points simultaneously, which we'll explore later. The amount of data processed at once significantly influences the network structure. Imagine trying to predict the color of a single pixel in an image versus predicting the content of the entire image. The latter requires a more complex network capable of handling much more information. A good rule of thumb is to provide the network with enough information comparable to what a human would need to make a similar prediction. Before designing a neural network, understanding the shape of your data is crucial. Data shape refers to the number of data points being processed at once. For instance, if your input is a single value, like the temperature, and your output is also a single value, like the predicted energy consumption, your network will have a different shape than one designed to process an entire image at once. At the heart of a neural network lies the concept of weights. Think of weights as adjustable knobs within the network. These knobs determine how the input data is transformed into the output prediction. In a simple network with one input and one output, a single weight controls the relationship between the two. These weights are what the network learns to adjust during the training process. Predict step. The first phase in the predict, compare, learn machine learning paradigm, where a model takes input data and generates an output prediction. Data shape refers to the structure of the input and output datasets, specifically the number of data points being processed at once, which dictates the design of the neural network. Weights knobs the adjustable parameters within a neural network that define the mapping from input data to output predictions. They are the knobs that the network learns to adjust. This section introduces the foundational concept of a neural network by demonstrating the simplest possible model: a single input multiplied by a single weight to produce a prediction. We'll use a Python code example to illustrate this core mechanism, building upon the prior concept of a knob, now formally termed a weight. Our simplest neural network consists of a single input, a single weight, and a single output prediction. The core operation is defined as: here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. The knob from previous discussions is now formally introduced as a weight, the adjustable parameter in the network. The weight is the single adjustable parameter, or knob, that scales the input data to produce the network's prediction. By the end of this section, you should be able to understand the fundamental mathematical operation, input weight, at the heart of the simplest neural network. Recognize the role and significance of a weight as the primary adjustable parameter in this basic model. The following Python code demonstrates the prediction equals input weight formula, showing how a single input data point is processed to generate a prediction. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Here, we initialize the weight variable to 0.1. This represents the adjustable parameter of our simple neural network. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This code defines the neural network function. It accepts two arguments: input, the data point, and weight. Inside the function, the input is multiplied by the weight to calculate the prediction, which is then returned. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. We create a list called number oftos containing sample input data. The first element 8.5 is assigned to the input variable, representing the single data point for this prediction. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1pagecode. The neural network function is called with the input 8.5 and the weight 0.1. The result, 8.50.1, is equal to 0.85, is stored in the pred variable. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1pagecode. The calculated prediction 0.85 is printed to the console. This example uses several key programming constructs, function definition, def, to encapsulate the network's logic. Variable assignment for storing data and parameters. Arithmetic operations, multiplication for the core computation. List indexing to access specific data points. Input, a single numerical value, e.g. 8.5, representing a data point. Output, a single numerical prediction, e.g. 0.85, the input multiplied by the weight. This model is highly simplified. Real neural networks involve multiple inputs, weights, biases, activation functions, and multiple layers. The weight value, 0.1, is arbitrary. In practical machine learning, this weight would be learned through a training process. The text explains the fundamental concept of a neural network as a simple input-weight operation, defining weight. The Python code directly implements this concept, providing a concrete example of the neural network function and reinforcing the flow from input to prediction via the weight. A neural network, at its simplest, is a system of weights that multiply input data to produce a prediction. Let's break down these core components. Input data. This is a numerical value measured from the real world, something easily knowable like temperature, a batting average, or stock price. Weight. Think of this as a knob or parameter within the network. It scales the input data to generate a prediction. Prediction. This is the output of the neural network based on the given input data, often expressed as a likelihood or a specific value. Neural networks learn through a process of trial and error. They make a prediction, compare it to the actual outcome, and then adjust their weights to improve accuracy for future predictions. This process of comparison and adjustment, while not explicitly demonstrated in the code below, is fundamental to how these networks learn. The following Python code demonstrates the simplest form of a neural network. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1pagecode. Let's walk through this code step by step. Weight initialization. We start by setting weight equals 0.1. This single floating point value embodies the current state of our extremely simple neural network. Neural network function definition. The neural network function takes two arguments: input, the data point, and weight. Inside the function, it calculates the prediction by multiplying the input by the weight and returns the result. This multiplication is the core operation of this simple neural network. Input data preparation. We create a list called numberoftos containing sample data. We then extract the first element, 8.5, and assign it to the input variable. This represents the single data point we'll feed into our network. Making a prediction, we call the neural network function with our input, 8.5, and the predefined weight, 0.1. The function returns the calculated prediction, 0.85, which we store in the pred variable, outputting the prediction. Finally, we print the value of pred, 0.85, to the console. This is the output of our neural network. Key considerations. This example represents the most basic form of a neural network, illustrating only the predict step. The weight is manually set and doesn't adapt or learn in this code. The input is a single number, simplifying the process to a single multiplication. Real-world neural networks often handle much more complex data. This simple example provides a foundational understanding of how a neural network takes input, applies a weight, and generates a prediction. It serves as a starting point for exploring the more complex and powerful capabilities of neural networks. This section clarifies how the simple single-weight neural network we've introduced actually works. It multiplies the input by a weight, effectively scaling it. We'll explore the roles of input as information and weight as knowledge, using the analogy of a volume knob to understand the weight's impact. We'll also highlight the network's stateless nature, its inability to remember previous inputs. The core function of this simple neural network is multiplication. It scales the input. It takes an input data point and multiplies it by a weight. This scaling can either amplify or diminish the input depending on the weight's value. At its interface, a neural network receives an input variable, representing information, and a weight variable, representing knowledge. It then produces an output or prediction. This fundamental input-weight-output structure remains consistent across all neural networks, regardless of their complexity. The weight acts like a volume knob, controlling the sensitivity or strength of the connection between the input and the prediction. A larger weight amplifies the input's influence on the prediction, making it more sensitive to changes in the input. Conversely, a smaller weight reduces the input's impact, making the network less responsive to it. Finally, it's important to understand that this neural network is stateless. It processes one input at a time and retains no memory of previous predictions or inputs. It only knows the current input. This characteristic implies that if we want the network to exhibit any form of memory, even short-term, we need to implement mechanisms like batch processing to feed it multiple inputs in a structured way. Scales the input. This refers to the multiplication of the input data by a weight, effectively increasing or decreasing its magnitude. Input variable. Information, the data provided to the neural network for processing. This is the information the network works with. Weight variable. Knowledge, the learned parameter within the neural network. This represents the knowledge the network applies to the input to make a prediction. Volume knob. Analogy and analogy to help visualize the weight's function. It controls the sensitivity or amplification of the input's influence on the prediction. The following Python code demonstrates this simple neural network's architecture and prediction process. Here is code. To get the code, please check onepagecode.supstok.com or visit the YouTube channel 1pagecode. First, we initialize the weight to 0.1. This single weight is the core of our network. Next, we define the neural network function. This function takes the input and weight as arguments, calculates the prediction by multiplying them, and returns the result. We create a list number of those to simulate having a data set. We then select the first element, 8.5, as the input to our network. This demonstrates how the network processes one data point at a time. Finally, we call the neural network function with our input and weight. The function returns the prediction, 0.85 in this case, which we store in the pred variable. Function definition, def, variable assignment, arithmetic operations, multiplication, list data structure, list indexing. Inputs, a numerical value for input, e.g. 8.5, a numerical value for weight, e.g. 0.1. Outputs, a single numerical prediction, e.g. 0.85. This code demonstrates the neural network processing a single data point at a time. It explicitly shows the multiplication operation, which is the fundamental operation of this simple network. The simplicity highlights the network's stateless nature. It has no memory of past inputs or predictions. This section introduces the concept of neural networks handling multiple input features to make more informed and potentially accurate predictions. Single features are often insufficient for complex predictions. Neural networks excel by accepting multiple data points simultaneously, combining their intelligence to generate a more nuanced output. Each input feature has a corresponding weight, determining its influence on the final prediction. This process utilizes a weighted sum operation, a core concept in multi-input neural networks. Multiple inputs, providing several distinct pieces of information, features, to the neural network at once for a single prediction. Weighted sum, the core operation in a multi-input neural network where each input is multiplied by its respective weight, and the results are summed up to produce the final prediction. By the end of this section, you should be able to understand why multiple inputs improve neural network predictions. Grasp the conceptual model of a neural network processing multiple inputs. Recognize that each input feature requires its own weight. The following Python code demonstrates a simple neural network taking multiple numerical inputs, multiplying each by a corresponding weight, and summing these products to generate a single prediction. We begin by initializing the weights. Each value in the weights list corresponds to the importance or sensitivity of a specific input feature. In this example, we have 3 weights. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. The sum function calculates the weighted sum of 2 lists, the inputs and their corresponding weights. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This function first uses assert to ensure the input lists have the same length. Then, it iterates through the input list, multiplying each element AI by its corresponding weight by and accumulating the sum in the output variable. Finally, it returns the calculated output. The neural network function represents the core prediction logic of our simplified network. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This function takes the input features and weights as arguments and calls the sum function to compute the prediction, which is then returned. Let's define some sample input data. Imagine we are predicting something based on 3 features. Toes, perhaps a measurement related to feet. Rec, possibly win-loss record. And fans, number of fans. Each list represents data collected across multiple games. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. For a single prediction, we take the first element from each list and combine them into the input list. Now, let's use the neural network function with our prepared input and weights to make a prediction. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This code calls the neural network function, passing the input and weights, and prints the resulting prediction. Here's a step-by-step breakdown of the weighted sum calculation for the given inputs and weights. Inputs: 8.50, 0.65, 1.20 weights, 0.1, 0.2, 0.0, 8.50, 0.1, equals 0.85, Toes prediction. 0.65, 0.2, equals 0.13, Warrek prediction. 1.20, 0.0, equals 0.00, and Fan's prediction. Total prediction: 0.85 plus 0.13 plus 0.00 is equal to 0.98. The number of weights must match the number of input features. A weight of 0 effectively nullifies the corresponding input feature's influence. This simplified model assumes a linear relationship between inputs and the prediction. This is a crucial simplification and a starting point for understanding more complex models. This section explains how a neural network handles multiple inputs to make a prediction. The core mechanism is the weighted sum, also known as the dot product. Each input is multiplied by its corresponding weight, and these individual products are summed up to produce a single prediction. We'll use vectors to represent both the input data and the weights. A vector is simply a list of numbers. For example, 8.5, 0.65, 1.2 could represent the input features of a single data point. Similarly, the weights are also represented as a vector. The multiplication between inputs and weights happens element-wise. This means that the first element of the input vector is multiplied by the first element of the weight vector, the second by the second, and so on. The weighted sum, or dot product, is formally defined as follows. Weighted sum equals input sub 1 slash sub weight sub 1 slash sub plus input sub 2 slash sub weight sub 2 slash sub plus plus input sub/sub weight sub/sub. Let's illustrate this with Python code. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Here, sum A, B takes two vectors, A and B, as input. It first checks if the vectors have the same length using an assert statement. Then, it iterates through the elements, performing element-wise multiplication and accumulating the sum in the output variable. Now, let's see how this sum function is used within a neural network. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. The neural network function takes the input vector and the weights vector as arguments and calls the sum function to compute the prediction. Let's define some sample data and weights. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Now, we can use the first game's data as input. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This code demonstrates how the neural network takes multiple inputs, applies weights, and calculates a prediction using the weighted sum. Each weight acts like a volume knob for its corresponding input. A larger weight amplifies the input's influence on the prediction, while a smaller weight diminishes it. A weight of 0 effectively ignores the input. The dot product also provides a measure of similarity between the input and weight vectors. A higher dot product suggests greater alignment or similarity between the two. The sign, positive or negative, of a weight also carries meaning. Positive weights contribute positively to the prediction, while negative weights can be interpreted as a not operation, reducing the prediction. The magnitude of both the input and its corresponding weight determines the overall impact on the final prediction. It's crucial to remember that weights have fixed positions within the vector. Shuffling them changes the network's behavior. Multiple inputs, complete runnable code. This section consolidates the concepts of a multi-input neural network into complete, runnable Python code. We'll first implement the network using basic Python lists and loops, then introduce NumPy for a more efficient approach. This implementation uses standard Python lists and a custom function for the weighted sum. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Here, sum calculates the weighted sum of two lists. The neural network function uses sum to compute the prediction. We define input data from multiple games, but use only the first game's data for this prediction. The weights determine the importance of each input feature. Now, let's achieve the same result using NumPy. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This version uses NumPy arrays and the efficient dot method for the dot product. This is significantly faster and more concise than the basic Python implementation, especially for larger datasets. NumPy is a cornerstone of numerical computation in Python, offering optimized functions and data structures for machine learning and scientific computing. Notice how the core logic remains the same, but the implementation is streamlined with NumPy. This highlights the importance of NumPy in making our code more efficient and readable. This section introduces the concept of a neural network producing multiple, independent predictions from a single input. This architecture behaves like several disconnected single-output networks operating in parallel. We'll use Python code to demonstrate this, performing element-wise multiplication of a single input value with a vector of weights to generate a vector of predictions. Several key concepts underpin this type of neural network. Multiple outputs from a single input. A neural network can generate multiple distinct predictions from a single input data point. Think of it as evaluating different aspects of that single input, each resulting in a separate prediction. Independent predictions. Unlike networks with multiple inputs where predictions are combined, e.g., through a weighted sum, each output prediction in a multiple output, single input network is entirely independent. Each output is calculated solely from the single input and its corresponding weight, without influence from other outputs. Simplicity of augmentation. This architecture is conceptually and implementation-wise simpler than a multiple input scenario due to the independence of the outputs. By the end of this section, you should be able to understand how a neural network can generate multiple predictions from single input, grasp the concept of independent predictions in a multiple output network, recognize the underlying mathematical operation, element-wise multiplication, used for this type of prediction. The following Python code demonstrates a neural network taking a single scalar input and producing multiple scalar outputs, each calculated independently using its own weight. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Here, weights is a list where each element represents the weight for a specific output. The neural network function accepts a single input in the weights vector and calls the elemental function to compute the predictions. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. We select the first element, 0.65, from the Warek list as the single input for our prediction. This input, along with the weights, is passed to the neural network function. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This function takes a scalar number, the network's input, and a vector, the weights. It iterates through the vector, multiplying the number by each element of the vector. The resulting products are stored in the output list. This effectively performs element-wise multiplication of the scalar input with the weight vector, where each element in the output list represents an independent prediction. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This illustrates the individual multiplications performed by elemental. The single input, 0.65, is multiplied by each weight, 0.3, 0.2, 0.9, to generate three separate predictions, 0.195, 0.13, 0.585. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. The pred variable, returned by elemental, holds the list of independent predictions. Printing pred displays these multiple outputs. The code utilizes several important programming concepts. Functions, def used to encapsulate the neural network logic and the element-wise multiplication. Lists, used to represent the weights and output predictions. Loops, for loop used to iterate through the weights for element-wise multiplication. Scalar vector multiplication, the core mathematical operation. Inputs, a single scalar value, e.g. 0.65, representing a win/loss record. Outputs, a list vector of multiple scalar predictions, e.g. 0.195, 0.13, 0.585, where each element is an independent prediction derived from the single input and its corresponding weight. Independence of outputs. Each output is calculated independently of the others, using only the single input and its associated weight. Contrast with multiple inputs. This architecture differs significantly from multiple input networks, where inputs are combined via a weighted sum. Here, predictions are generated in parallel, not summed. This section introduces the most general form of the simple neural network covered so far, one that handles multiple input features and produces multiple independent predictions. This is achieved by connecting every input node to every output node via a unique weight, effectively performing a weighted sum for each output based on all inputs. The accompanying Python code demonstrates this concept using a vector matrix multiplication approach. A neural network can process multiple input features and generate multiple distinct predictions simultaneously. This architecture represents a more comprehensive and practical application of neural networks. The key principles are: each input node is connected to every output node. Each connection has its own unique weight. The prediction for each output is calculated as a weighted sum of all inputs. The weights are structured as a matrix. In our implementation, WeightSync defines the weight connecting the inputted th input to the outputted th output. The weights variable is a list of lists, a matrix. Each inner list contains the weights for a specific output node applied across all input features. For example, weights 0 contains the weights for the first output, applied to input 0, input 1, and so on. For each output, a weighted sum dot product of all inputs is performed using the corresponding set of weights. This process is repeated for every output node. This is equivalent to a vector matrix multiplication, where the input vector is multiplied by the weight matrix to produce an output vector of predictions. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. First, we define the sum function, which calculates the dot product of two vectors. This is a fundamental building block. Next, the vectmapmul function performs vector matrix multiplication. It iterates through each row of the matrix, representing the weights for a specific output, and calls sum with the input vect and the current row of weights. This calculates each individual output prediction. The neural network function is the main function. It takes an input vector and the weight matrix and calls vectmapmul to compute the predictions. Finally, we set up sample input data and a predefined weights matrix. The input represents features like toes, wreck, win/loss record, and fans fan count. The weights matrix connects these inputs to outputs representing predictions for hurt, win, and sad. Running the neural network function with this input and weight produces a prediction vector, as shown in the example output. This code demonstrates how a neural network can take multiple inputs and generate multiple outputs using vector matrix multiplication, effectively implementing a weighted sum for each output based on all the inputs. This section explains how a neural network with multiple inputs and multiple outputs works. The core mechanism is a series of independent weighted sums, dot products, one for each output. We'll explore how matrices and vector matrix multiplication form the mathematical foundation of this process and see how it's implemented in Python. Imagine each input node having a connection to every output node. Each connection has an associated weight. While you can think of 3 weights coming out of each input node, it's more helpful to visualize 3 weights going into each output node. This perspective clarifies how each output is calculated. This network calculates multiple predictions from multiple inputs using a series of weighted sums. Each output is the result of a weighted sum of the inputs, using a different set of weights. Let's define 2 crucial concepts. Matrix, a list of vectors. In our network, the weights variable is a matrix. Each row of this matrix represents the weights for a specific output. Vector matrix multiplication. This operation involves taking an input vector and performing a dot product with every row vector in a matrix. This is precisely how our network computes multiple predictions from multiple inputs. By the end of this section, you should be able to understand that a multi-input, multi-output network performs multiple independent weighted sums. Conceptualize a matrix as a collection of weight vectors, one for each output. Understand vector matrix multiplication as the process of performing a dot product between an input vector and each row of a weight matrix. The following Python code demonstrates a neural network handling multiple inputs and outputs using vector matrix multiplication, building upon the sum dot product function. This function, reused from previous sections, calculates the weighted sum dot product of 2 vectors. It's a fundamental building block for calculating individual output predictions. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This function performs vector matrix multiplication, the core operation for multi-input, multi-output predictions. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This code takes an input vector, vect, and a weight matrix, matrix. It initializes an output vector and then iterates through each row of the matrix. Each row represents the weights for a specific output. For each row, it calculates the dot product between the vect and that row using sum, storing the result in the corresponding index of the output vector. This function orchestrates the prediction process. It simply calls vectmatmul with the input vector and weight matrix. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Inputs, input, a list representing the input features, e.g. 8.5, 0.65, 1.2. Weights, a nested list matrix, where each inner list represents the weights for a specific output, e.g. 0.1, 0.1, minus 0.3, 0.1, 0.2, 0.0, 0.0, 1.3, 0.1. Output, a list of numerical predictions, one for each output node, e.g. 0.555, 0.98, 0.965, could represent predictions for hurt, win, and sad. The code, particularly vectmatmul, directly implements the series of weighted sums and vector matrix multiplication concepts. It clearly shows how each output prediction is calculated via a dot product of the input vector and the corresponding row, weight vector, of the weights matrix. This section introduces the fundamental concept of stacking neural networks, where the output of one network layer serves as the input for a subsequent layer, creating what is known as a hidden layer. This architecture is essential for modeling complex patterns in datasets and is implemented through consecutive vector matrix multiplications. We'll explore this concept using both basic Python and a more efficient NumPy implementation. The core idea is to feed the output of one neural network, or layer, as the input to another. This creates a stacked architecture, allowing for deeper, more complex models capable of learning intricate patterns. The intermediate layers within this stacked architecture are called hidden layers. They represent an internal transformation of the data, learning features that are not directly visible in the input or output. The output of the first layer, input to hidden, becomes the input for the second layer, hidden to output. Simple single-layer networks are often insufficient for highly complex datasets, such as those encountered in image classification. Stacking layers allows the network to learn progressively more complex features, enabling it to model intricate relationships within the data. The mathematical engine behind stacking is consecutive vector matrix multiplications. Each layer performs a vector matrix multiplication, which is essentially a series of weighted sums, to transform its input into its output. Stacked neural networks. A neural network architecture composed of multiple layers, where the output of one layer feeds directly into the input of the next. Hidden layer. An intermediate layer of neurons in a neural network that processes input from a previous layer and passes its output to a subsequent layer, without being directly exposed to the external input or output. IT. Input to hidden weights the matrix of weights connecting the input layer to the first hidden layer. HBWGT. Hidden to prediction weights the matrix of weights connecting the hidden layer to the output, prediction, layer. The following Python code demonstrates a two-layer neural network, input, hidden output, using sequential matrix multiplications. First, we define two weight matrices, I, input to hidden, and HBWGT, hidden to prediction. These matrices are stored in a list called weights. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This function takes the input data and the weights. It calculates the hidden layer output, hid, by multiplying the input with int. Then, it calculates the final prediction, pred, by multiplying hid with HBWGT. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Here, vectmatmul performs the vector matrix multiplication, and sum calculates the weighted sum of two vectors. Now, we'll prepare sample input data and call the neural network function. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This code takes the first data point from toes, warec, and fans as input, feeds it to the neural_network function, and prints the resulting prediction. The same two-layer network can be implemented more efficiently using NumPy. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Key differences and benefits of using NumPy. Efficiency. NumPy provides optimized C implementations for array operations, resulting in significantly faster computations. Conciseness. NumPy's method simplifies the code for matrix multiplication. Transposition. Note the .t used to transpose the weight matrices. This is crucial for correct matrix multiplication in NumPy, ensuring proper alignment of dimensions for the vector matrix product. This NumPy version provides a more practical and performant approach to implementing the same neural network, bridging the gap between theoretical understanding and real-world application. This section introduces NumPy, a fundamental Python library for efficient numerical operations, especially for handling vectors and matrices. We'll explore creating NumPy arrays, performing element-wise operations like multiplication and addition, with NumPy's broadcasting rules, and executing .products, matrix multiplication, emphasizing the importance of shape alignment. The code examples will directly illustrate these concepts. Before diving into the code, let's define some key terms. Vector, a list of numbers. In NumPy, a vector is often represented as a 1D array or a 2D array with one row or column. Matrix, a list of vectors. In NumPy, a matrix is a 2D array defined by its dimensions, rows, columns. Element-wise operation, mathematical operations, plus, dash, /, performed between corresponding elements of arrays. For element-wise operations, arrays need to have the same number of columns, or one array can have only one column, allowing for broadcasting. Product, matrix multiplication, a specific type of multiplication between vectors and/or matrices. In NumPy, the product is calculated using the method. The number of columns in the left operand must equal the number of rows in the right operand. Scalar, a single number. Scalars can be broadcast across an entire vector or matrix during operations. Broadcasting. NumPy's ability to perform operations on arrays of different shapes by implicitly stretching the smaller array to match the larger one, following specific rules, e.g., scalar vector or vector matrix element-wise operations. The following Python code demonstrates these concepts. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This code first imports NumPy as NP. Then, it demonstrates creating vectors A, B, and matrices C, D, E using np.array, np.zeros, and np.random.rand. Note how np.zeros, 2, 4, creates a matrix filled with zeros, while np.random.rand, 2, 5, creates a matrix with random values. The print statements display the created arrays. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Here, the operator performs element-wise multiplication. NumPy's broadcasting is demonstrated. The scalar 0.1 is multiplied with each element of vector A, and similarly with matrix C. Notice how IB multiplies corresponding elements of vectors A and B. The code also shows vector matrix multiplication, where vector is broadcast across the rows of matrix C. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. This section demonstrates the method for matrix multiplication. Pay close attention to the shapes of the arrays. The inner dimensions must match for the product to be valid. The shape attribute displays the dimensions, and T transposes a matrix, swaps rows and columns. The last example intentionally demonstrates a value error that arises when attempting a product with incompatible shapes. This reinforces the importance of shape alignment in NumPy operations, especially for products. This summary consolidates the key concepts we've explored, emphasizing that neural networks predict through repeated weighted sums of input data. Surprisingly, complex networks arise from simple underlying rules applied repeatedly. This process of prediction is called forward propagation. Let's break down these core components. At their core, neural networks make predictions using a fundamental operation, the weighted sum of input data. This simple calculation is the foundation upon which all the complexities of neural networks are built, regardless of how intricate they may seem. We've seen how even sophisticated neural networks are constructed from a small set of simple rules and operations. These basic building blocks are combined and stacked to create increasingly powerful and intricate architectures. The intelligence or predictive power of a neural network hinges on the specific values assigned to its weights. These weights represent the learned knowledge of the network, shaping its responses to different inputs. The entire procedure of a neural network taking input data and generating a prediction is called forward propagation. This term describes the flow of information, specifically activations, moving forward through the network's layers. Weighted sums, the central mathematical operation in neural network prediction. Each input value is multiplied by its corresponding weight, and these products are summed to create an output. Forward propagation, the process where input data flows through the network's layers, undergoing calculations with weights to produce a final prediction. Information moves strictly from input to output. Activations, all the numerical values produced within a neural network during prediction, excluding the weights themselves. Activations are specific to each prediction, representing the intermediate and final outputs of calculations. Understand that repeated weighted sums are the basis of neural network prediction. Recognize how complex network architectures are built by combining simple rules. Grasp the crucial role of weight values in the network's predictive ability. Define and understand forward propagation as the prediction mechanism. Identify activations as the dynamic numerical outputs during forward propagation. Anticipate the next step, learning how networks adjust their weights for accurate predictions, using similarly simple combined techniques. Looking ahead, we'll delve into how these weights are adjusted, a process called weight learning, allowing the network to make accurate predictions. Just like the prediction process itself, weight learning relies on simple techniques combined in powerful ways.